All right, there's a lady inside that machine. All right, and I will be standing up, so even though, it's on Zoom, I do want to stand up and conduct the class as we always do. I'll just try to talk loud. If you ask a question, I'll repeat it to the person on Zoom. So we are recording now. So, and it always sticks a little when you first start. I don't know why, but now, shock. So the next exam, chapters 13, 14, and 15 will be either this Friday or Monday. Do you have a preference? Do you have a preference? It'll be this Friday or Monday. Monday. Okay, so we'll make it Monday then. All right. The exam will be Monday. So we'll finish chapter 15 today or Wednesday. All right. And then we'll have the exam on Monday. Is that good? Are you good with that, Diana? All right. So I'll also make the active chem homework due Monday too. But try to get, it's only 15 problems, but try to work on that this week. And then I can help you if you get stuck. And I want to continue mentoring sessions, so hopefully Ivana or Akia will come. Otherwise, Aoife and I will get together briefly. Yes, question. I think so. Yeah. Yeah. All right. But some of them are calculations. All right. So let's review a little bit of what we did while you were away. I mean, just before we went, review some of the things from last class, but I'm going to, let me see, get that out of the way. Okay, is that out of the way now? Good. So we looked at strong acids and strong bases, weak acids and weak bases, and buffers. Oh, got stuck again. Click it, and it gets unstuck. There you go. Okay, so remember how we find the pH of a strong acid and a strong base. One step for a strong acid. Remember, we just take the negative log of the strong acid. For strong base, we have to do two steps. First, find the pOH, negative log of the strong base, and then pH plus pOH is 14. We figure out the pH. And then for a weak acid and weak base, and you'll be given these formulas. You can find the hydronium concentration using this formula, Ka times the concentration of the weak acid, and then you take the square root of that product. For a weak base, you find the hydroxide concentration first. It's the square root of K sub B times the concentration and molarity of the weak base. That's starting to ring a bell? Look familiar? All right. And then we got the buffer, Henderson-Hasselbalch equation. To find the pH of a weak base of a buffer solution, you take the pKa plus the log of, remember this is the base, it doesn't have the H there, and this is the acid, it has the H. So the acid over the base. Remember they're conjugates, and we can also write it like that. Conjugate base over weak acid, or it could be weak base and conjugate acid, either way. But it's the base over the acid. And so this formula will be given to you, this formula will be given, and this formula will be given to you. And remember, base, acid. Okay, sound good? Then we said the pKa, because we need the pKa, is just a negative log of the key of Ka. And I said a p of anything is the negative log. So the p of Professor Coppola is the negative log of the concentration of Professor Coppola's. All right. Remember that relationship. Hydronium ion concentrations times OH concentration equals 10 to the minus 14. And that's also equal to the K sub W of water. Now remember, that's at room temperature. That's at room temperature. All right. And here's a new one I'm going to add. pKa plus pKb is equal to 14. And so it has to do with mathematics when you take, anyway, it's just true. So this relationship, when we find the negative log of each, we can add them. We get the pKa plus pKb equals 14. Just like the pH one. pH plus pOH is 14, pKa plus pKb is also equal to 14. I'm not going to derive that for you, but it's true mathematically. Okay, so remember what we were doing. Titration is a way of determining an acid-base concentration in a solution. It was invented by our friend, at least my friend, Mr. Guy, who also said that if pressure and temperature are directly proportional for gas, pressure and temperature are directly proportional. All right. And I want to clarify something. I really liked your question, Yufei. I got to speak louder, I realize, because I'm not at the mic. I'm not at the mic there. But the pH, where a particular indicator changes color, is called the endpoint. And I want to amplify this to make it clearer. The equivalence point is when the moles of acid equal moles of base. Probably should stand over here. I'm closer to the microphone. Good idea. All right. So the end point is the color change. And now I want to give several examples. They change colors as the pH changes, but there's different kinds of indicators. Like here's one. And so this is the very acidic color, and that's the very basic color. And this is sort of in between. This is over 2 pH units. And this is called bromthimal blue. I don't have the pHs there. Good morning, Ivana. Here are several other indicators. And notice that the endpoints are different. They change color at different pHs, and sometimes they change again. You don't have to memorize this. It's only for illustration purposes. This is the one you're most familiar with, phenolphthalein. It's about 7, where it changes color. So is that clear now? The end point is when the indicator changes color, but it depends on the indicator. Okay? Equivalence point is moles acid is equal to the moles base. See the difference? Does that help? But that was an excellent question. I love that question. Now, this is kind of a fun one. Anyone ever do this? You just take cabbage and you boil it, and you pour out the juice, and it's an indicator. And it has all these different colors as you go from acid. These are the pHs here. Acid to base. Look at the different colors. When it's pH 11, it turns that color. And that's just regular cabbage juice. So that's a natural indicator. Pretty cool, huh? You want to try that, Diana?
So you just boil it?
You boil it in water, and then you pour out the
color.
the juice,
Mhm.
and that's an indicator. So you can put in bleach, maybe,
Mhm.
see what color changes.
Mm.
Or another sample, pour in, I don't know what kind of acids you have at home.
Mhm.
I can't think of any offhand, but. And then it's a similar thing. Now we're going the other way. This is the acid, lemon juice, vinegar, Sprite. You see how it changes colors?
Mhm.
Kind of fun. All right. You don't need to memorize any of that. It's just an illustration. Good. And then remember, I'm going to go through this quickly because we've already covered this. So when we have a strong base up here and a strong acid down there, we start adding drop by drop, and eventually it gets neutralized, and the next drop changes color. So this is going to be the acid is clear, and then when it becomes a base, it changes color. Approximately 7. I think you use that in the lab, right? Was it phenolphthalein?
Yeah.
Yeah. All right. Good. And again, the end point is the color change. All right. And then we looked at the shapes of curves when we graph titrating an acid with a base. So, again, let me come over here so they can hear me on the recording. So, what we did was we graphed a strong base being added to a strong acid, and then we did a strong base to a weak acid, and we have different shapes. You need to know the shapes of the curves. So we graphed it. So strong base to a strong acid. Strong acid was HCl. Strong base was NaOH, and we added different amounts of it. And remember, when we did that, we end up with this type of graph. And I'd like you to know the shape of the curve. It's kind of an S shape. And where's the pH? At the equivalence point, can somebody tell me? What's the pH? 7. When you have a strong acid and a strong base, the equivalent point to pH is 7. And it has this kind of a shape. Okay? We looked at a strong base with a weak acid, we get a different shape. Strong base to a weak acid. So now we have a weak acid in here, and we're adding a strong base, and what kind of a curve do we get? It's not quite, here's the strong acid, strong base curve, the S shape. This one, it's a little bit shorter, and it looks like that. This is the buffer region. Now remember what the buffer region is, the pH doesn't change much. And the equivalence point on this baby is 8.80. So strong base with a strong acid, when they hit the equivalence point, it's not 7. This is the buffer region. So we have a flattening of the curve. So, I asked this on the exam, what kind of titration is that? A strong base with a strong acid or a strong base with a weak acid? Right. Recognize it that way. Equivalence point is 7. And over here, this is going to be the titration of the weak base. Excuse me, the strong base with a weak acid. And the way you can recognize it is that you see there's a flattening of the curve, whereas here, it goes straight up. But here, it's more of a flattening in the buffer region. And this could be the buffer equation. Remember what a buffer is. It's got a weak acid and its conjugate base. This is the acid, conjugate base. They differ by H plus, right? This one has an H one, this one doesn't. This gives it away. That's the acid. And coming back the other way, this is going to be the base because it's going to accept an H. The strong, weak acid, conjugate base. They differ by H. The shape is a little bit flattened here. And what's the equivalence point? Much greater than 7. Number of moles acid and number of moles base become equal and the pH is greater than 7. All right, now we're actually going to go through something a little bit complicated. Now I'm going to slow down. Now I'm going to slow down and go through this slowly. So what I just did, we just reviewed. We already covered it. Please review this after class. Now we're starting off with 20 milliliters of 0.3 molar acid. And we're going to titrate it with 0.5 molar NaOH. So this is where our acid is, right there. 0.3 molar acid. Okay? It's a strong acid. No, excuse me. It can be a strong acid in one case and a weak acid in the second case. First, we'll do the strong acid. So that is going to be the molarity in the burette. So that's the flask, and that's going to be the burette. 0.5 molar always. We're going to go through 2 sets of titrations, one with a strong acid, one with a weak acid, but the base is going to be the same concentration, 0.5 molar NaOH. Okay, so strong acid with a strong base, 20 milliliters at that concentration, titrated with that concentration. Then we're going to go through it again, titrating the weak acid with a strong base. In that case, we're going to need to know the Ka and the pKa, but we're giving us the pKa. We can find the Ka from the pKa, and we'll go through that. So we're going to calculate the pH at each of various points of titration. I'm going to start off with no base, then I'm going to add 10 milliliters, then 12 milliliters, and then I think 20 milliliters. Then I'll do the same over here. And we're going to calculate the pH in each case. Notice, by the way, we're always going to have this number of moles of acid. Why? Because 20 milliliters divided by 1,000 is 0.02 liters. We converted milliliters to liters times, what's the concentration? 0.3 moles per liter. Liters cancel. 0.02 times 0.3, we get 0.06006 moles of acid in every case. But in the first case, it's a strong acid. In the second case, it's going to be a weak acid. Okay, so fasten your seatbelts. Here we go. Here we go. Everybody with me? So here's our general strategy. The initial concentration we're going to look at, which is just going to have acid and no base. Then we're going to start adding base, and we call that pre-equivalence. It hasn't reached the point where moles of acid are going to equal moles of base. Then we're going to hit a point when we add a certain amount of base, the moles of base are going to equal to the moles of acid. That's the equivalence point. And then we're going to keep on going, and we're only going to have moles of base, and it's called the post-equivalent. So we're going to have the initial concentration, which is 0 base, pre-equivalence, equivalence point, and then post-equivalence. And each step, we're going to calculate the pH. That's just a preview. So here we go. Good morning, Akil.
Morning.
We are going to titrate the strong base with the strong acid. SP, strong base, strong acid. Strong base is NaOH. Strong acid is HCl. Again, this is always going to be the same. We're starting with this much, 20 milliliters of 0.3 molar HCl, and we're going to have 0.5 molar NaOH. As I said before, we're always going to have 0.06 moles of HCl, but because HCl it completely dissociates, right? Remember that? We're going to get H plus Cl minus, and these are the same. That's the same. But we can also say this represents 0.06 moles H plus. In every case, that's what we're starting with. By the way, Akil and Ivana, I'm recording the class for the people that are coming back from the mission trip, and we have one student who got injured over the break, so he's watching on Zoom. Okay, so we're on Zoom right now. All right. So that's what I just said. We actually have 0.06 moles of H plus all the time. All right, number one, when we have no base, we haven't added anything yet, we're in strong acid land. And as we're going to see, when we add 10 milliliters of base, we're still in strong acid land. When we get to 12 milliliters of that concentration of base, we're in neutral land. Okay, because the equivalence point is the number of moles of H plus are equal to the number of moles of OH minus. And just the same as the strong base, just the same as the strong acid, the strong base, when that breaks up, you're going to get an Na plus OH minus, and these are the same because this completely dissociates. So the moles of this is equal to the moles of that. All right. And then the last case, when we had 40 milliliters of strong base, we're going to be in strong base land. So the first step we're going to do, we're not going to add any base and calculate the pH. In the second case, we're going to add 10 milliliters of the base. In the third case, 12 milliliters. In the fourth case, 40 milliliters. And in each case, we are going to calculate the pH. Any questions so far? You with me? This table's not level, so we just did an experiment. I already knew it's not level. If there's anything I put on there, it rolls off. All right. Commercial. You have a commercial. Better late than never, but never late is better. To be on time, come early. Okay? All right, end of commercial. Here we go. Now we're going to calculate the pH of that. Notice we have the concentration inside this little flask here is 0.3 molar HCl. There's no base, so how do we calculate the pH of a strong acid? Does anyone remember? The negative log of the concentration. So Ife, oh, you said the negative, right? That's okay. Well, at least she made a attempt, and that's good. It's the negative log of the concentration. What's the concentration? Diana. 0.3. So that's all we do. And again, it completely dissociates, so it's the H plus ions. So we just take the negative log of the concentration of HCl. Remember that in a strong acid, you can just take the starting concentration, 0.3 molar. Take the negative log of 0.03. And first we get the log of 0.03 is a negative 0.52, then a negative of that is 0.52. So we're in strong acid land, ladies and gentlemen. Would you agree? That's a very low pH. We're in strong acid land. Yes. Any questions on that? So before you add the base, it's just pH of a strong acid. We already know how to do that. Nice. But you do need to know this formula, negative log of the concentration of a strong acid. All right. So this scenario, it's just the pH of a strong acid alone. All right. Now we're going to add 10 milliliters of NaOH. Okay. Now in this case, now we're adding base. So we got to figure out the moles of acid and the moles of base. The moles of acid and the moles of base. So I already said there's 20 milliliters in the flask of 0.3 molar. And now we're adding 10 milliliters of 0.5 molar. Okay, so that's the acid is here, and the base is up there. So we want to get the moles of each. How do we get the moles of each? Again, these completely dissociate. So the moles of this will be the moles of that. And the moles of this will be the moles of that. So how do we get the moles? Well, it's just molarity times volume. And we've already done this. I converted 20 milliliters divided by 1,000, I get that. 0.020 liters. That's the molarity. So this is going to be liters times moles per liter. Liters cancel, and we get that. Are we good with that? Do the same thing for the base. So how much do we add? 10 milliliters. 10 milliliters divided by 1,000 is equal to 0.010 liters times 0.5 moles per liter. Liters cancel. We get that number of moles. Is everybody with me? We calculated. So each mole of acid neutralizes each mole of base. So what's left over? What's left over? I take the difference. So what is it? Yes. So the difference is 0.01 moles of acid. All the base has been neutralized and we're left over 0.01 moles. But before we can find the pH, we need the concentration in moles per liter. But now we just added 10 milliliters to 20. So Gabi, what's the total volume now? We started 30. So what we did was, does everyone see that now? The new volume is 30. We had 10, we had 20 in the flask, and we added 10 more. So we got 30. Now we can get concentration. How do you find concentration, Gabby? You take what divided by what? How do you find concentration? Number of moles per liter. So how do we find it here? We have this number of moles, and we have that volume. I converted it to liters. Now 30 milliliters divided by 1,000 is 0.0 liters. So how do I find the molarity? He's chewing ice, it's okay. I take what by what? Yeah, so I take 0.001 moles divided by 0.03 liters. Everybody that's with you on that? That's the new molarity of the acid. And Diana, how do we find the pH of a strong acid? Now we know the concentration. How do we find the pH? It's the negative log of what? Want to take a guess? So, here's my little guy. How do you find pH of a strong acid?
Minus log.
Of that, okay? So you need to know that. So we're going to take pH is the negative log of the H plus concentration. We just computed it to be 0.033. So I take the log of that and then the negative, and the pH is 1.4A. And we're still in strong acid land. Even though we had 10 milliliters of base, we're still in strong acid land. And by the way, we have a video that goes over this, what I'm doing. So if you want more reinforcement, that link, that's the link, that titration of a strong base with a strong acid. There's a video of this to go over it again. So in this case, we added 10 milliliters of base. We figured out moles of acid, moles of base, and we had this much left over. Then we had the new volume, and we took moles divided by liters. We got the molarity, and then we found the pH of that. Good? Good. All right, so we're still in strong acid land. So we went from, let me just go back again real quick again. Sorry about that. We went from a pH of 0.52, and now we go to a pH of 1.48, but we're still in strong acid land. Okay? Now we're going to move to neutral land. We're going to land. Now we're going to see that the moles of acid are going to be the moles of base, because now I'm going to add 12 milliliters to this puppy. And in here we got 20. Now I'm going to add 12. I just added 10. Now I'm going to add 12. So I'm increasing it by 2. Now watch what happens. Let's get the moles of acid and the moles of base. Everybody with me? This is the volume in liters times 0.3. We got that number of moles, 0.006. And it turns out if we convert 12 milliliters to liters divided by 1,000, right? And you multiply that by 0.5, guess what you get? The same. So what's the difference? Goose egg. The big goose egg. A guy in high school, he'd always say, you know, if you got a 0 on an exam, I got the big goose egg, which is not something to brag about, but it's a goose egg. So what does that mean? Well, right away, if there's equal amounts of acids and base, you just know the pH is 7. It's neutral. We're neutral. Oh, I made one of these too. Where's my neutral land? Where's he hiding? There we go. We're in neutral land now. However, if you want to actually calculate what the pH is, we just can do this. We can see, everybody see the concentration of the acid is equal to the concentration of the base, moles divided by volume. And when that's equal, remember this formula. If these two are equal, and the product is 10 to the minus 14, each has to be 10 to the minus 7, right? And the pH of 10 to the minus 7 is 7. It's basically 1 times 10 to the minus 7. So if you type that into your calculator, it's going to come out to be a negative 7, and then you put a negative sign, and it's 7. Okay, so now we're in neutral land. So we went from adding no base to 10 milliliters of base, and now when we hit 12 milliliters of base, we're in the neutral land. Now, what happens if I keep adding base? What do you think is going to happen to the pH? If I keep adding base, it's going to what? Yes, we're going to move to baseline. We're going to go to strong baseline. We're going to strong baseline. I'm making a fuss, so remember. So we're going to strong baseline next. So let's go through the same thing again. Again, this is on a video, strong base versus strong acid. Now we're going to add 40 milliliters of base. So let's calculate the number of moles of acid and base. We know the moles of acid already. Everybody good with that? Now we're going to take 40 milliliters and convert it to liters. It becomes 0.040 liters. We divide it by 1,000 times 0.5. Now what do you get? 0.020 molar base. So if we take the difference of those two, I'll do it for you. Does everybody see that all the base 0.02 is bigger than 0.006? But we've neutralized all the acid, and how much base do we have left over? We have that much left over. Ivana, what's the total volume? If I added 20 milliliters to 40, if I added 40 milliliters to 20, what's the new volume? 60. So the new volume is 60 milliliters. I divide by 1,000, convert it to liters. Now I can take moles divided by liters, right? If I take moles divided by liters, I get that. Now here I have to do the pOH first, so watch out. Because of OH. So how do we get the pOH, Ife? Of the concentration of OH minus. Do I have that on here? Yeah, I'm going to have it right here. You need to know that. We have to get the pOH first. We'll take the negative log of 0.233. I take the log of 0.233. I get a negative number, and the negative of that is, we're not done yet. We want the pH. How do we get the pH, Akil? You know the pOH, how do we get the pH? Subtract from 14. Yes. Got it. Nice. Nice. So 14 minus 0.63, it's going to be 13.4. And ladies and gentlemen, we are in strong baseland. We are in strong baseland. Okay. Everybody with me? Now I'm going to do a recap of what we just did. Please review this tonight or today, first chance you get. And work on your homework. That'll help you understand it even better. You got it, Gabby? You looking good? Okay. Again, we have a video that goes over this for reinforcement. So what do we do here? Well, in each case, we had 20 milliliters of 0.3 molar HCl. That stayed the same. Well, it's actually here, it's clear in the beginning. It ends up like that. First case, strong acid land, and the pH was 0.52, and that's how we got it. The second case, we're still in strong acid land. We do the same thing. 1.48. In the third case, 12 milliliters, we're in neutral land because we have equal numbers of moles of acid and base, and the pH is 7. In the last case, we added 40 milliliters of base, and we ended up with a pH of 13.4. First, we had to get the pOH. Good? So that is calculating the pH as you titrate something. Okay, now it's going to get a little bit complicated. It's going to get a little bit complicated with the weak acid and with the weak acid in there, it's going to get complicated. Now we're going to use acetic acid in here. The weak acid, right? How do we know it's a weak acid? not on the list. Remember the strong acids, perchloric acid, hydrochloric acid, sulfuric acid. And what was the other one? Sulfuric and perchloric. Okay? That's your acid, Ivana, perchloric. By the way, do you have time for a mentoring session in 5 minutes? Good. And then on Friday, we'll do you, okay, Keel, because Wednesday's complication. All right, are you ready for this now? This is a little more complicated. Please review it again. A little more complicated. We're still going to do moles of acid and moles of base. Figure that out. But we're going to have an equilibrium situation. And we're going to have to end up using these formulas over here. I don't know if you can see that from here. We're going to be using these formulas because we're going to be using a weak acid. And then we're going to use the Henderson-Hasselbalch equation, which I don't have on here, when we hit buffer land. Okay. In the first case, it's not too bad. We have a weak acid, and we haven't added any base yet. So what land are we in then? We are in, I have a sign here. We are in, nope, that's the wrong one. Where's my weak acid land? Buffer, weak base land. There you go. Excuse me, we're in weak acid land. How do we know we're in weak acid land? Because we're using acetic acid. This is found in vinegar. That's the weak acid. So the pH should be, you know, higher, quite a ways above 1. Well, let's see what it is in this case. Notice they're giving us the pKa. We're going to need that when we hit buffer land. But we're also going to use the pKa to find the Ka by working backwards. So how many moles of acid do we have? It's the same. It's the same, but here's our equilibrium equation. We're going to need this, and we're going to need this for the Henderson-Hasselbalch equation, because we're going to take base over acid in the Henderson-Hasselbalch equation. This is given, but we don't know what this is yet. We got to figure that out, because it doesn't completely dissociate like the strong acid. So we're going to find the pH first for the weak acid. We haven't added any base yet. All we have is this. What's the equation to find the pH for weak acid? It's our shortcut formula, which I'll give to you on the reference page. You don't have to memorize it. Active Chem is going to use the ICE table every time. You don't have to do the ICE table. We have this equation. So we got to find the Ka, we got the pKa, and we're given this. We're given HA, right? It's it is 0.3 molar acetic acid. How do we find the Ka? We got to work backwards. So that's our formula. We know this is 0.3, because that's given. But we don't know Ka, but we do know pKa. And remember, pKa is the negative log. The P of anything is a negative log. The P of me is a negative log of my concentration. So we got to work backwards here. We know pKa, we don't know Ka. But the way to handle this is multiply both sides by -1. Does everyone see what I did? Then take the anti-log of Ka. When I take the anti-log of both sides, the log goes away, you're left with Ka. And the anti-log of this, remember what you do, you type in -4.74, and then put inverse log, and you're going to get that. It should make sense. It's a weak acid. That's very small. But now we know Ka, yes? Okay, so plug in those numbers. Is everybody with me? Concentration is given to the weak acid. We just figured out the Ka. We we had to get it from the pKa by working backwards. I multiply these two together, and then I take the square root. And when I do this, I multiply these two together on my calculator, I get an answer, and then I hit the square root button, and this is what I get. Now, how do I find the pH, Gabi? If I know the acid H3O concentration, how do I find the pH? Just the negative log of that, right? So in the weak acid situation, you've got to find the hydronium concentration with this equation first. Right? So pH is going to be the negative log of that. And it's going to come out to be negative 0.263. And then I take the negative of that and I get 2.63. And that puts me in weak acid land. That's weak acid land. 2.63 is a weak acid. Strong acid would be closer to 1. That was pretty easy. Just the pH of a weak acid. We have to use what I call the shortcut formula. Don't have to use the ice table again. We did that. Pardon me. Now, are you ready for the next step? Because we're going to move into buffer land. Yvonne, are you with me? Review this again. At home, okay? Or first chance you get. Now we're going to add 10 milliliters of base, and that's going to put us in buffer land. By the way, again, this is covered on this video. The video here is a weak acid and a strong base. In the video, they do use the ice table, but we don't need to do that. We just use this. We're going to end up with the same thing, the shortcut formula. Ready for buffer land? Here we go. Now we're going to be in buffer land. Now we're moving to buffer land, okay? Buffer land. You start off the same way. And now we're going to use the pKa because in the Henderson-Hasselbalch equation, we need the pKa, which, by the way, I will give you the Henderson-Hasselbalch equation on the exam. Don't have to memorize it. So let's get the moles of acid, right? Same way. Yes? Let's get the moles of base. Well, we've got 10 milliliters of NaOH. We convert that to 0.010 liters times 0.5 molar, and we get that. Now here's where it gets complicated. We have to write the equation, the equilibrium equation for a weak acid. We have to write the equilibrium equation because it's a weak acid and it doesn't completely dissociate. So everyone see what I just did there. We have acetic acid and it's a weak acid, so it doesn't completely dissociate. And after a certain time, it starts going in the reverse direction. And once you hit that equilibrium, no changes anymore. So, how much acetic acid did we start with? Notice that's the weak acid and the conjugate base, right? They differ by an H plus. And we're going to use that in the Henderson-Hasselbalch equation. So we start off with 0.6 moles of that, 0.5 moles of that. And how much, before we add those together, we have none of that. Then when we mix them together, what's going to happen? Well, the 0.005 moles of base are going to neutralize that amount of acid, and we're left with just 0.01 moles. All of the base will be used up because it's going to neutralize it. How much CH3COO minus will we have? Well, we had 6. If we have 6 of that, let me show you this with the pointer. If we have 0.6 here, we're gonna end up with 0.6 there. However, wait a second, what did I just say? Five moles of this, we're gonna get 0.5 moles of that. That's where it gets complicated. Take a look at that for a minute. Why is that? Because we used up 0.05 here, we used up 0.05 there. That means we're going to form 0.05 there. And so that's why we end up with 0.05 moles. And so that's the tricky part. Just like before, as you remember, whatever is used up is formed on the other side. We're using up that much of that, and so we're forming that much of that. Now, how much acetic acid are we left with then? How much OH minus are we left with? And how much of that are we left with? This fits nicely with our Henderson-Hasselbalch equation. Why? You know the pKa. Which of these two is the base? Which is the base? That one. So it's 0.005, and the acid is 0.01 moles. Now, we could divide each by the volume. The new volume is what? The new volume is 10 plus 20 is 30. But since it's the same in both, we can skip that step because it's going to cancel out. It's not going to make any difference. It's going to cancel out. So in other words, I could say 0.05 moles divided by 30, but it's exactly 0.03 liters, and the same for this. But you don't have to do that because you'll get the same answer. But we're just going to take 0.005 divided by 0.001. Let's plug those in. pKa is given. Base over the acid. How do I know that's the base? Because that's what's left over. And this loses the H plus. It's always the base over the acid. So we're going to take the log of this, and that we're going to take this divided by that, take the log, we get 0.7. And so the answer is going to be 5.44. And so we are in buffer lane. So what's different about this? This is the most complicated one of all. What's different about this? We have an equilibrium situation. And we know that this amount is used up. Why? Because it's neutralized by the base. All of the base gets used up because it neutralizes 0.05 of the acid. So it forms, that's how much base is formed. If that is used up, that's how much is formed. That's the tricky part. You need to study this. All right, now, again, we talk about in the video. Now we're going to reach the equivalence point. What is the equivalence point again, Ife? What does it mean? Equal parts base and acid. So Ife said, when there's equal parts base and acid. But the pH is not going to be 7. If you remember earlier in the class, the pH is above 7 when you titrate a strong base with a weak acid. We go through the same procedure of figuring out moles of acid and moles of base. Because now, when I convert this to that, it's when I convert 12 milliliters to liters, I get 0.012 liters. I multiply these two together, and I get 0.006 moles. now let's show our equilibrium equation. What did we start with? That number of moles. How about here? The same. And that means we're going to get, and this is 0 before we add them together. Once we add them together, if that much is used up, how much of that is formed? Diana. You got it. And what are we left with? Only base. So that makes it much easier. If you only have base, we just have to take the moles divided by the volume. Gabi, what's the new volume? What's the new volume? 20 milliliters plus 32, plus 12 is 32. So we're going to have to use our shortcut equation. But one more thing is we got to do here. So we're going to calculate, just like Gabi said, 0.006 divided by 32. But we got to get the KB. But we have the KA. We already computed that. Whoops, that's a typo. That should say computed. I'll fix that. Okay, I can't fix it now because Zoom won't let me. Thanks a lot, Zoom. As I come out of it, it'll mess everything up. So I have to leave it. I'll fix it. That's a typo. That's a P. All right. Anyway, so we remember that Ka times Kb, I think I have it on here. Right here. Ka times Kb is 10 to the minus 14. So can everybody see that I can find Kb by taking 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Now we got Kb, and now we can use that formula. So as Gabi just said, the volume is 32 milliliters. I convert it to liters by dividing by 1,000. We take the number of moles over the volume. And it's going to be, that's the concentration of the weak base. Now I plug everything into this equation. We got the Kb. We got the B. Multiply these two together, take the square root. And I'm going to get that. And then first I have to find the POH. So Akil, how do I find the POH of that? Right. We have to do the POH, plug that puppy in, with the negative log of that. And when I take the log of this number, it'll be a negative, and then a negative of that makes it a positive. And the POH is 4.99. And then Ivana, how do I get the pH? How do I get the pH?
From the POA?
Yeah. Right. So I take 14 minus 4.99 and notice what the pH is. It's way above 7, even though this is the equivalence point. There's that video. Okay, so the weak acid with the strong base is a little more complicated. But work on your active chem, review the notes from today, and let me know if you have any questions on Monday. And ladies and gentlemen, I have good news. Class is over. So thank you for the privilege of your time. Have a wonderful week and welcome back. I miss you. Well, it's going to be Monday. Decided to have the exam on Monday. Let me just stop the share and turn it off. Okay, goodbye, everyone who's on Zoom.